Well, thank you guys for inviting me. I appreciate having the opportunity to speak about infrared camera resolution today and its impact on temperature measurement. It's really one of the more important considerations if you're buying an infrared camera or perhaps already own one, and you're not sure if you have sufficient resolution for your application. Now, that's especially true for those of you in the electric power industry where our targets are not at, let's say, 3 to 5 feet, but perhaps 30 to 50 feet or even further. It's because resolution, among other things, impacts our ability to not only see important thermal details on a target, but also measure temperatures accurately. And I guess the plan is to run about maybe 20 to 25 minutes or so, and we'll take questions here afterwards. Before we get into it, just some quick background here. I'm with the Infrared Training Center based out of our Boston regional facility here in Nashua, New Hampshire. We're part of FLIR Systems, but handle specifically the certification training for thermographers using any type or manufacturer of infrared camera. And this training is essential if you want to get the most out of your investment in the technology. I've been teaching thermography now for about 16 years to professionals across a variety of industries. My primary responsibilities include level 1 and level 2 infrared certification courses that I run throughout the United States, including those classes here in Nashua. And besides training, I also run ITC's live and on-demand webinars, produce infrared training videos, and manage our social media efforts. So today we're going to be discussing the impact of resolution on temperature measurement. I think this example was really the essence of what we're going to talk about. Of course, what type of camera you own matters, but it's also about the size of the target and the distance to it, which affects our ability to resolve things properly. Now, even though the moon is almost 240,000 miles away, it's a diameter of about 2,160 miles, makes it large enough that we can still see it with a certain handheld thermal imagers. In this case, it's a FLIR T640. And we see two thermal images here. The rainbow palette on the right shows a maximum box temperature of 148 Fahrenheit compared to an apparent spot reference of about 5 below, which is deep space. So we're definitely picking it up. And my point here is that we can see the moon, but perhaps not the International Space Station or a telecommunications satellite, because even though it's much closer, it's too small of a target. So that's the essence of resolution in many ways. What's the size of the target? How far away are we? And what type of resolution do we have on our thermal imager? Now, to understand resolution and temperature measurement, we first need to understand that a thermal image, just like a visible light photo you captured with your smartphone, is made up of pixels. Now, I've got an iPhone 8 Plus here, which I think has a 12 megapixel camera. That means there's 12 million detectors inside the device behind the lens, which captures visible light and creates an image. Now, infrared cameras have a detector as well, but instead of seeing visible light, the difference is that they see heat. The other significant difference here that you'll notice is that for almost all handheld thermography products, we're not talking about megapixels, but instead thousands of pixels, depending on the model of camera. Here we see 4 examples, and the first 3 are some of the more common that you'd find in condition monitoring or building diagnostics. Quite simply, the horizontal value is the number of detectors across the horizontal, the vertical, the number in a row vertically. You multiply them together and you get the number of detectors for that particular camera. Now, more pixels means more detail. And we can see that very clearly here in this next example. Here we have 2 images of the same residential home captured in cold weather from the exterior using 2 different cameras. Now, standing at the same distance for both using a similar lens sizes for each camera. On the left is an 80 by 60 focal plane array. On the right is 640 by 480. That means there's 640 detectors across the horizontal and 480 on the vertical. With more detectors, we can discern smaller areas of thermal detail. Now, when it comes to how a thermal imager is spec'd out, most often the manufacturers list the detector size as the resolution of the camera. But detector size is only part of the resolution equation. We also have to consider lens size, and with that, what's known as the field of view. So the field of view is everything that is on your screen that represents the entire field of view of everything you're seeing, and that's the acronym here, FOV. Lenses come in a variety of different sizes or fields of view. The standard lens runs about 25 degrees. You might see some variation on that. Some are 23 or 24, but it's around 25 degrees or so. You can have a wide angle lenses. Those might be 45 or even 80 degrees. And a telephoto lens probably around 12 or even 6 or 7 degrees, perhaps in some cases. So to explain that, the field of view, it's the horizontal field of view that's actually spec'd out with that degree size. So if we're looking at this from above, let's say, a 25-degree field of view is horizontally an area of 25 degrees across. It's an angle of measurement that we're seeing. And so it's the detector size in conjunction with the size of the lens which provides us with our spot size ratio, or what's called the SSR, which is defined as the ratio of the distance from the camera to the object compared to the size of the spot being measured. And here we see three different views of the same target. One with a telephoto or 12-degree lens, that's there on the left, the 25-degree standard lens in the middle, and the 45-degree wide-angle lens on the right. It's the 12-degree lens which provides us with the best resolution, giving us the best detail of this particular target. So let's dive into this a little bit further to better understand resolution with the following illustration. I'm going to pretend for a moment that we don't have a 640 by a 480 camera. Let's say we don't even have a 320 by 240 or perhaps even an 80 by 60. Instead, for illustrative purposes here, we have a 9 by 7 focal plane array. That's 63 pixels. There's 9 across the horizontal and 7 on the vertical. The instantaneous field of view, or what's called the IFOV, is the projected size of what one pixel is seeing within the overall field of view. And that's that red square there in the center. What's one pixel picking up? What's detecting? Well, can we see it? So if the field of view is the entire 25 degrees, the IFOV is what that one pixel is seeing. So depending on how many detectors you have, obviously you're going to be seeing different sized spots within the target. Both change with the lens. So check out this example here. Another way to think about it. Let's say you're trying to capture a thermal image of your house. We're going to use this 9 by 7 focal plane array, the 63 pixel camera. But instead of standing on the front lawn, let's say the house is down the block. All right? It's a little ways away there. Looks really small from our perspective here. If I look at this house with this 9 by 7 camera, one pixel will pick up the house. We're not going to get a lot of detail here. It's going to look like a hot dot in the thermal image. To get better resolution, if I get closer to the house with that camera and I put more detectors on the target, as we see here in this illustration, I capture more detail. And this is the essence of resolution. How much detail are we capturing at a given distance with a given lens and focal plane array size? So this is the shot of the side of my house here in New Hampshire. Got some insulation related issues. This was taken last winter. Cold weather conditions. Looking up here at this shed dormer on the left with a 25-degree lens, on the right with a 12-degree lens. Both of these images were taken with a T640 thermal imager. So it's a 640 by 480. And what I want to do is capture more detail. So to bring in this hypothetical illustration here from earlier, to get more resolution, better detail, I need more pixels on the target. And I can either get closer, or in this case, if I use a lens with a more narrow field of view, in this case a 12-degree or a telephoto lens, I can capture more detail on the target. Now, just a quick sidebar here for those of you that maybe are looking to purchase an infrared camera. Most manufacturers express the IFOV in units called milliradians, or MRAD. This is an angle of measurement. It's a geometrical measurement corresponding to the detector size projected through the lens, what we were just talking about here a moment ago. Let me explain just briefly what a milliradian is. If you take a circle, all right, just think of a circle, 360 degrees. An arc of a circle that is the same length as the radius creates a 1 radian angle. That's a 57-degree angle or so. What's 1 milliradian? Well, it's just 1/1000th of that slice of pie. Think of it as a really, really small slice of pizza. And it's an angle of measurement, and that's how they spec these out. And so you'll see this in the specification, the data sheets for thermal imagers, 2.6 milliradian or 1.36 milliradian. This is for the IFOV, the instantaneous field of view. Basically, the smaller the number, the better the resolution of the infrared camera. So that's something to keep in mind if you're purchasing a camera. If you want good resolution, buy the thermal imager with the lower milliradian value. because it corresponds to a pixel size, seeing a smaller area within the scene. Now, the instantaneous field of view is just about detection, the IFOV. It's just about seeing the target. That is, are we close enough to pick it up? When it comes to measuring temperatures with something such as a spot meter that you might find either in many cameras or in the FLIR tool software, we need more pixels on the target. And this is where measurement field of view comes into play. In level 1, we simply dub this as filling the spot. To get the most accurate temperature reading, you need more pixels on the target. And the spot meter is not 1 pixel in size. It's a matrix of pixels. And to get the most accurate reading, you have to fill up that circle completely. To illustrate this, I'm going to use in our training lab here in Nashua, we've got a fuse cutout that's mounted on the back wall. And this is one of the demonstrations that we'll run during a level 1 training class here. And it's great because there's like a 1-inch target on that. It's hard to see if I can drag the mouse over it. It's right there. It's black tape wrapped around it. That's a target we're going to look at here in this next sequence. Hopefully this video will play. We're going to run this through. I've started off here at about 3 to 4 feet or so. The spot meter there showing us a temperature of about 99.4 degrees Celsius. So we're what, almost 212 degrees Fahrenheit in this example. But this is at 3 to 4 feet. I'm going to play this through. And what we're going to do here is zoom in digitally, use the digital zoom on these cameras. Oops, let me go back for a second. So watch this. As we go from a regular to a 2-power zoom, you notice that the spot meter seems to increase in size. What's happening here is the digital zoom is an electronic magnification of the display. It's actually not zooming us in, it's just blowing up the pixels. And so here at the 4-power zoom, what we can see here is we've completely filled that spot. And we're getting a temperature reading of about 99 degrees or so. Well, at this point, I stepped back to about 30 feet from the target and looked at the same spot using the same camera. And notice the temperature difference much lower, about 74 degrees. What happens is I haven't filled that spot circle completely. So I don't have sufficient resolution to get an accurate temperature measurement. We have to get more pixels on the target, filling that circle essentially to get the most accurate temperature reading possible. So there's just another example of it in this situation here at about 5 feet in the left-hand image and then 32 feet on the right side. And you can see the temperature differential there. So resolution is essential to getting accurate temperatures with an infrared camera. This was from a class I taught in Fairfax, Virginia a couple of years ago. One of the students, we were on a little exercise, went out back behind the hotel, and they noticed a tensioning disconnect here up on the telephone pole here, up on the wires, was running a little bit hot. In fact, the image on the right here shows it to be out of range at about 320 degrees. Now, with this particular camera, they didn't have sufficient resolution to pick it up, but in terms of like measuring an accurate temperature reading, but they were able to find it. Using a higher resolution camera, we were able to dial that in a little bit more closely and got a reading of over 518 degrees, something that we weren't seeing with a lower resolution camera. This was a great find and likely, in all likelihood, probably even hotter than this, given the fact that our distance to target is fairly significant in this situation. And so what we're trying to illustrate here is that if you're in, let's say, the electric power industry and you're doing utility-based work, having great resolution is essential to getting the most accurate temperature reading and the best assessment of what's happening with the component. To further illustrate this, I shot this outside last week. I had a 320 by 240 camera on me with 2 different lenses that I was able to use. But I wanted to illustrate again the differences in lens and how lens is essential, the lens size. If you're using any kind of thermography for outdoor electrical work, a telephoto lens, something that's even less than 25 degrees, really important. On the left was a 320 by 240 with a 45-degree lens. And if you notice the spot temperature measurement here in the left-hand image, it's 38 degrees. Now, the ambient temperature here outside was 57. Unless they're running cold water through those power lines, there's no way it can be 38 degrees. It's impossible. What that tells me is that the spot meter is measuring more than just the target. Remember that circle from a moment ago? we're getting more than just the target here. We're actually capturing some of the atmosphere. And in reality, it's really deep space. If it's a clear sky, we're seeing some of that sort of infiltrating into the image there and giving us a lower temperature value. On the right, with a 25-degree lens, a slightly narrower field of view, we can now see a temperature of about 58 degrees on that spot. But we can do better. In this situation, with a 640 by 480 thermal imager, here's a sequence of images here, starting with a 45-degree lens. If you notice in the upper left-hand corner there, a max temperature of 181.4 degrees. That's inside that box that you see there, 181.4. Well, if I switch to the 24-degree lens, the temperature increases to 188.5. What we're getting is more pixels on the target. With more pixels on the target, we're getting more information, we're getting better detail, and we're getting a more accurate temperature reading. And even better than this, a 7-degree lens, we now see a temperature reading of 192 degrees Fahrenheit. More pixels, more detail, better information. Essential, that showing us that resolution really matters. Now, resolution aside, you have to know what you're doing as a thermographer. So having the proper training is really important as well, because even with, you get resolution, you still have to know to operate the camera properly, and these are things that can affect your temperature measurement accuracy also. One of the biggest ones that we sort of emphasize in our level 1 classes is having proper focus. If your image is out of focus, you're not going to get the right detail. Things are going to look soft. What many people don't know is that being off slightly on your focus will also affect your temperature measurement accuracy. And this is, again, where a high-resolution camera can help, because it's easier, I should say, to get better focus with a higher resolution system, because you can dial it in and get a sharper image there. But we got to work on focus. Focus has a significant impact on the accuracy of temperature values. Emissivity is another one, something else that we emphasize in level 1 training. This is my grill in my backyard. It's running. It's over 300 degrees. We can see that on the right-hand side here on the flat black painted surface. Temperatures that are actually out of range on this particular camera, but on the shiny metal top of the grill, only about 90 degrees Fahrenheit. That's not correct. That's actually the same temperature here as the spot on the side, but due to the low emissivity and high reflectivity of that surface, our numbers are not accurate in this situation on that shiny metal. So understanding emissivity is important. We do this with bus bar lab demonstrations in our level 1 courses. Shiny copper bus bar has a very, very low emissivity, doesn't radiate its heat energy well or efficiently at all. And what appears to be, let's say, a 5-degree difference here between two mock-up phases here on an electrical bus is really a temperature difference of almost 75 or 80 degrees Fahrenheit. And so for an outdoor substations with lower emissivity surfaces, you got to be careful, not just about resolution and focus, but also about emissivity factors as well. And one thing we want to stress too is that the temperature difference measurements are not independent of emissivity values. So you have to realize that when you're in an outdoor substation, if you don't know your emissivity of your target, just guessing, you're likely not going to have the right temperature difference measurement. And that's something that's really important for thermographers to understand. As our emissivity gets lower, our temperature difference gets larger. So without having that emissivity locked in many cases, we're just guessing. And then indirect heating is another thing that we have to be careful with. You think of large substation equipment like a transformer, an oil-filled circuit breaker. We have our indirect heating lab that we do in our level 1 classes here. This is a light bulb in a box. It's an incandescent light bulb. On the outside, the maximum temperature is 114 degrees. And on the inside, it's close to actually 400 degrees. It's out of range on this particular camera. And my point here is that you're looking at a transformer, in this case a load tap changer. And you see an elevated temperature here, not much, but just a little bit, 16 or 17 degrees or so. You have to understand that it's not 16 or 17 degrees, it's a lot hotter than that on the inside. We can see that here with the coked up oil in this shot that was taken after it was de-energized and taken out of service. So my point here is that resolution is very important, but there are many other factors as well, and that is thermographers, we have to understand all of it to get the most out of our investment in the technology. So having a great camera with good resolution, very important, but also understanding the physics behind how temperatures and how infrared camera sees temperature, really important as well. And so that brings into this part of the discussion here, temperature measurement accuracy and severity criteria. If you're using temperature to sort of prioritize your anomalies and the things that you find, just be careful and make sure that you really understand that you are getting an accurate temperature, because there are factors here that will affect the accuracy of your temperature measurements when you're in the field, and it's essential for thermographers to understand that. And so if you want more, the Infrared Training Center offers a lot of on-demand webinars and live tutorials throughout the year. If you go to our website, infraredtraining.com/webinars, you'll find those listed. We have information on this particular topic and others that are accessible completely free. And you can watch it as many times as you want. Of course, we have our training schedule off our main website as well. And if you want more, coming up this fall, we're going to be in Austin, Texas, September 11th to the 14th for the Information Conference. This is the world's largest conference for thermographers. It's a networking event as well. Whether you work in electrical, commercial building, or optical gas imaging, it's really a one-of-a-kind conference for anyone who wants to come. 60 paper presentations we've got set up, training clinics, poster sessions. As I mentioned, the networking opportunity as well. Whether you're a beginner or a seasoned thermographer, it provides attendees with an opportunity to learn from the top experts in your industry. It's going to be September 11th to the 14th in Austin, Texas, and you can head to information.org to sign up and book your hotel. And I know we've got several papers on electric power that are planned for this event, so I would definitely check it out if you're in this field. And of course, you want to get social with ITC, you can join us online at any of these channels: Twitter, Facebook, YouTube, Instagram, or LinkedIn.